പ്രിയ വിദ്യാർത്ഥികളെ, കൊറോണ വൈറസിൻ്റെ വ്യാപനം കാരണം കേരള സർക്കാർ നമ്മുടെ ക്ലാസ്സുകളൊക്കെ റദ്ദ് ചെയ്ത് നിങ്ങളെല്ലാവരും വീട്ടിലാണ്. നിങ്ങളെല്ലാവരും പഠന കാര്യങ്ങളൊക്കെ ശ്രദ്ധിക്കുന്നുണ്ട് എന്ന് കരുതുന്നു. ഓൺലൈൻ രംഗം വളരെ സജീവമായ ഈ കാലത്ത് റെഗുലർ ക്ലാസ്സുകളിൽ വന്നില്ലെങ്കിൽ പോലും നിങ്ങൾക്ക് പഠിക്കാനുള്ള ഒരുപാട് അവസരങ്ങളുണ്ട്. നിങ്ങളെല്ലാവരും അത് പഠിക്കുന്നുണ്ട് എന്നും ഞാൻ ഉറപ്പായി വിശ്വസിക്കുകയാണ്. അപ്പോൾ അതിൻ്റെ കൂടെ തന്നെ കൊറോണ വൈറസിൻ്റെ മുൻകരുതലുകളെല്ലാം എല്ലാവരും എടുത്തിട്ടുണ്ടാകുമെന്നും ഉറപ്പാണ്. സർക്കാർ ഉദ്യോഗസ്ഥർ നിരന്തരം തരുന്ന നിർദ്ദേശങ്ങൾ എല്ലാവരും പാലിക്കണമെന്നും കൂടെ ഉണർത്തുകയാണ്. ഈ ഒരു ശ്രമം നമ്മുടെ റെഗുലർ ക്ലാസ്സുകൾ നടക്കാത്ത ഈ അവസ്ഥയിൽ കുറച്ച് ടോപ്പിക്കുകളിൽ നിങ്ങൾക്ക് ഒരു എക്സ്പ്ലനേഷൻ അല്ലെങ്കിൽ ഒരു ലെക്ചർ തരാമെന്നാണ് ഈ ഒരു ശ്രമത്തിൻ്റെ ഉദ്ദേശം. അപ്പോൾ ഇതിൻ്റെ ഭാഗമായി നമ്മുടെ പേപ്പറിൻ്റെ ന്യൂക്ലിയർ ആൻഡ് പാർട്ടിക്കിൾ ഫിസിക്സിലെ റേഡിയേഷൻ ഡിറ്റക്ടറാണ് ഇവിടെ ഇന്ന് കൈകാര്യം ചെയ്യാൻ ഉദ്ദേശിക്കുന്നത്. ഞാൻ പവർ പോയിൻ്റ് സ്ലൈഡ് വെച്ചിട്ട് നിങ്ങൾക്ക് ക്ലാസ് എടുക്കാൻ ഉദ്ദേശിക്കുകയാണ്. നിങ്ങളത് ഫോളോ ചെയ്യുമെന്ന് ഞാൻ കരുതുകയാണ്. ചെറിയ ചെറിയ ലെക്ചറുകളായിട്ട് നിങ്ങൾക്ക് ഞാനിത് പോർഷനാക്കി സെൻഡ് ചെയ്ത് തരാം. We will start with the radiation detectors. Radiation detectors, also called particle detectors, are instruments designed for the detection and the measurement of subatomic particles. Subatomic particles such as those emitted by radioactive material or produced by particle accelerators or observed in cosmic rays, such as particles include electron, proton, neutron, alpha, beta, gamma, or numerous mesons or baryons. The most detectors utilize the same principle for detection, that is production of excited or ionized atom by charged particle traveling through the medium. The ionized particle collected to produce an electrical signal. Radiation means maybe it's a charged particle like alpha, proton, or fast moving electron, or it may be uncharged particle like neutron, or maybe simply radiation like gamma radiations or X-rays, such as X-rays. The radiation interacted with matter in different form. So I will explain that interaction with using this diagram. Suppose alpha particle, alpha, you know, that is a helium-2 for nucleus. Helium particle can broken by a simple paper itself, but for beta, it's an electron beam, cannot block using a paper, but it can block using an aluminum sheet or aluminum material. And for the gamma, the photon, high energy photons, can block using lead. It cannot block paper or aluminum. So it means what? That radiation interacted with the matter in different form, different way. So radiation detectors, the main principle of any radiation detector is the interaction of nuclear particle radiation with the base material of the detectors. When a charged particle moves through the material of a detector, it can ionize or excite the atom or molecule of the substance of the detectors. Charged particle and gamma rays are capable of producing ions in the detector directly. But for neutron, which are uncharged particle, can detected using an intermediate reaction have to be used. Mainly particle detectors or radiation detectors are classified into gas-filled detectors such as ionization chamber, proportional counter, or Geiger-Müller counters are some example for gas-filled detectors. There are solid state detectors like scintillation detector, semiconductor detector, or Sarango detector. There are different chambers or detectors called bubble chamber. Is one type is bubble chamber. So the working of various detectors is based upon the one of the following three main characteristics like ionization or excitation, I have already told, fluorescence, or particle and rays affect the photographic light. So there are different type of output or output pulse we can get. So the different mode is a continuous mode or pulse mode. The main problem with the detectors in pulse mode is that two interaction must be separated by finite amount of time if they are to be produce distinct signal. So this interval of time between two pulse is called dead time of the system. Second interaction occur in this interval, its signal will be lost. If it occur close enough to the first interaction, it may distort the signal from the first interaction. Dead time of detector system largely determined by the components in the series with the longest dead time. GM counters have the longest dead time. GM counters have dead time ranging from tens to hundreds of microseconds. So the first type of material I am going to explain is gas filled detectors. The gas filled detectors consist of a volume of gas between two electrodes with an electrical potential difference applied between these electrodes. Ionizing radiation produces an ion pair in the gas. Positive ion attracted to negative electrodes, it means cathode, and electron or anion attracted to positive electrode is called anode, towards anode. In most detectors, cathode is the wall of the container that hold the gas and the anode is a wire inside the container. In this type of detectors, as a gas filled sensors is there and a cathode and anodes are there. So gas filled, the basic type of gas filled detectors are ionization chamber or proportional counter or Geiger-Müller tube or counter. When a uncharged particle passes through a gas filled detector, large number of atom or molecule are excited, which can de-excite with emission of a visible or ultraviolet photon. A number of atoms are ionized also, giving rise to primary ionization. So when an particle interacted with the medium, it get ionized. This ionization we call primary ionization. ഈ പ്രൈമറി അയണൈസേഷൻ നടന്ന ആറ്റംസ് എന്താ സംഭവിക്കാം, ഇതിൽ ഒരു പക്ഷേ ഇലക്ട്രോണും അയോൺസും റീകമ്പൈൻ ചെയ്ത് അതെന്ത് ചെയ്യും, വിസിബിളും അൾട്രാവയലറ്റ് ഫോട്ടോണെ പുറത്ത് വിട്ടിട്ട് അത് റീകമ്പൈൻ ചെയ്യും, റീകോമ്പിനേഷൻ റീച്ച് നടക്കും. അതല്ലെങ്കിൽ ഇലക്ട്രോണ് or ion can move towards the corresponding electrodes. Then ഇലക്ട്രോൺ ക്രിയേറ്റ് ചെയ്ത ഇലക്ട്രോൺ മറ്റ് ആറ്റവുമായി ന്യൂട്രൽ ആറ്റവുമായിട്ട് കൊളൈഡ് ചെയ്യാൻ സംഭവിക്കാം, വീണ്ടും കൊളീഷൻ സംഭവിക്കാൻ. അപ്പോൾ എന്ത് സംഭവിക്കും, നെഗറ്റീവ് കൊളൈഡ് ചെയ്തിട്ട് അവിടെ അയോൺസും ഇലക്ട്രോണും ആക്കി മാറ്റാം. പോസിറ്റീവ് അയോൺസ് മൂവിങ് ടുവേർഡ്സ് ദ negative electrode, that is it's towards the cathode. So the recombination may happen or it can move towards the electrodes. So the recombination rate is, we can express it as the recombination is proportional to or equal to alpha. It's a proportionality constant, is called recombination coefficient, and it's also proportional to the number of electron produced due to the primary ionization and number of ions it's produced. So this is the rate of recombination. So I already, when a potential is applied between cathode and anode, it produces an electric field in the counter volume. This electron and ion start moving towards anode and cathode respectively due to the effect of electric field. Therefore, recombination rate become less and the electron or ion get reached at electrode. The chance for reaching at electron is more. When ion drift towards the cathode with a velocity v, suppose the velocity v is equal to mu into E by P. The P is nothing but a gas pressure and E is the electric field and mu is the mobility of ion, is proportional to mu into root of E by P. Electron can get collected at anode in very small time period while ion take longer time. So consider a parallel plate ionization chamber. I will explain. So my parallel plate ionization chamber, this is separated with a distance d. Separated with a distance d, and it applied a potential V here. I consider a potential V grounded here, and this is a R resistance, it's a capacitance C, and a potential V is applied, a potential is reached here. Due to this E, here a electric field, uniform electrode V by D is there. That much electric field is there inside this volume. A gas is filled in this, in between this plate. Suppose a particle passes through the medium and it entered through this, I consider region x distance from the cathode. This is x distance from the cathode. This is x. So x distance from the cathode, and at this distance the primary ionization is happened. So it means what? Electron ion pair produced at this region. The produced electron moves towards anode and ion moving towards the cathode. So the electron moving towards anode. So at the, when the charge induced at anode is proportional to V minus Vx, because electron is starting from at a potential Vx and towards to the anode, and also ion induce a charge at cathode is proportional to Vx. So this is the idea. So total charge induced is same as induced by n0 number of electron reaching anode. So if suppose C is the capacitance of the anode, then anode potential changes. The potential changes due to the induced potential of electron is can represent as a value minus n0 into E by C. The potential induced by electron is much shorter time than that by ion induced charge. Induced charge leaks through the anode load R with a time constant Cr. If time constant Cr is less than the collection time of ion, suppose the collection time of ion is T prime, one observe only signal induced by the electrons. The full potential signal at anode can be observed only if the time constant Cr is much greater than the collection time of ions T prime. So this graphically I can represent that value. You can find this graph from the equation if you are from the textbook, if this is not much clear, or suppose yeah, this is maximum potential change, that is nothing but n0 into E by C, and this is corresponding to CR equal to infinity value, when this corresponding to T, and here I can and suppose two interaction I considered and B, and this point is T dash, and this is CR or RC is much than T prime point. In this region is CR is less than T prime and greater than T. So this is T delta V graph, shape of a signal at anode of ionization chamber. So that is, it's okay. So the signal produced at the anode is proportional to the energy dissipated by incident particle in the ion chamber. So I will explain once more. So ionization chamber used for the measurement of energy of charged particle. So actually the energy resolution follow the normal or Gaussian distribution. So the energy dissipation at the medium, that is in chamber, is proportional to actually sigma is the sigma by n0 is so called root of n0 by n0. So it's nothing but 1 by root n0 is proportional to 1 by root e, where sigma n0 is equal to root n0 is a standard deviation of n0 electron ion pair. So this is the theoretical resolution or energy resolution, but experimentally observed that energy resolution is much better than that of predicted by this relation. So this is explained, this problem is explained with a new factor. It's called empirical factor known as Fano factor. Fano factor. Using Fano factor, we can correctly explain the energy resolution, which should multiply by the variance. The Fano factor is multiplied with variance sigma n0 square. Sigma square is variance to give observed energy resolution. So it means what? Now the energy resolution can represent with a value square root of f into sigma n0 by n0 whole square. So nothing but R is equal to root of f by n0. This is so this is the basic idea of a gas field detectors. In the next video I will give the idea of ionization chamber, detailed idea of ionization. Okay, before that I will explain one more point. So this is the what I am explaining. This is one type is parallel plate shape and another is the cylindrical shape. Cylindrical shape, the surface itself act as a cathode and the center wire is an anode. Here also anode wire and cathode wire. So this is the all about the gaseous detectors. So here is what I am explaining is along x-axis is voltage applied and the y-axis is charge collected. So I already explained there are different type of gas detectors: ionization chamber, proportional counter, Geiger-Müller, all having the same idea, but the only the application level, and some are different. So all both the gaseous detectors can explain using this curve. So only the difference is the applying potential across the electrode is different. So first region here is, I call it just a recombination region. Here we are not bother about much about it. The second region, like a plateau, here the red color is beta and alpha with a different energy particle. So the plateau region is nothing but ionization chamber, and the linear region is a proportional counter region, and there is a limited proportional region is there. So we apply more potential than ionization chamber, that act as a proportional counter. If you apply much more potential, higher potential across, it act as a Geiger-Müller counter. So this is all about. Again, I will explain in detail in each portion in the next video. Thank you.